Okay, so this is the second time I'm doing this. So this is devlog 4B. I ran out of batteries the first time and it turned out to be way too long. So this one's actually going to be quite short, and I'm going to focus on making a map struct that we're going to use next time to add A-star pathfinding to our units. So let's get started. First thing we're going to do is add our map module, which doesn't exist yet, so we'll make a new one. And let's make sure that builds fine. It does. Yep. Okay. Looking at my notes, we're going to do the cell and the map cells first. Right, debug and clone, because we're going to create loads of these cells as empty. Vector 2, which means we need to add vector 2, and we also need rect 2 in there as well. And we are going to add map cells like this, which is going to have an inner vec of cell. To create one of these, we need to call with capacity, because we need to know, we're always going to know how big the map is. So because I've done this already, I'm kind of rushing through this a little bit, but I'm going to try to be coherent. So now we can create as many empty cells as the capacity. And okay, something is obviously wrong here. Map cells, there we go. And now we can add map cells to our map. We're also going to need to know the map size and the tile size. The tile size is just an X and Y, and the map size is an actual rect of a map. It's a bit odd to have two things called size that are of different types like that. But right, okay, so that's done. Next up, we're going to implement chords to index and index to chords. Okay, so let's implement our map. And we're going to add a new function as well. So we can start by passing in a bunch of chords. And these chords are going to come from the Godot tile map. And we also need the map size and the tile size. And here we can set the map size directly, same thing with the tile size. But for the cells, we need to do this. So we need to figure out the capacity, which is the map size width times the map size height, and that needs to be a U size. And we need to capture this because we're going to populate this here. So here we can say chords dot iter for each chord. You know what, this can all fit on one line. This doesn't have to be on several lines. We need the index, which we're going to get from the map dot chords to index. And then we can insert this into our map cells, which doesn't have an insert function yet. And we need to insert chords, vector 2. That's it. There we go. Okay, so we have an insert function. So then we can do map.cells.insert index and the chord. Now this function doesn't exist, chord index, and that's by the way is getting a reference, and that too. So we're gonna do this, dereference it right there. Now we need to add these chords to index, so that's what we're gonna do next. And we return a usize. And calculating the index is pretty simple. We say the chords x minus map size minimum x. And that's the x value, and then the y value is going to be the same. Y, there we go. And then we say index is the x plus y value times the width of the map. And then we're going to return the index as usize. Okay, so this doesn't do any bounds checking or anything like that. You can pass in an index that is vastly incorrect, or you can pass in coordinates that aren't part of the map. So if you pass in minus 5,000, it's still going to try to do that, and you're going to get some real gibberish numbers coming out of this. But just to be quick about it, getting this implemented again. So anyway, so we're doing this, and yeah, and the reason why we reduce the take the min x and min y is because you might have negative values. So if x is equal to -1 and the lowest value is also -1, so if min x over here, if that's -1, then you're gonna end up on 0. And the same thing applies for y. So if the smallest values are -1 and you pass in -1, you're gonna end up with 0, which would be an accurate index, right? So let's see. If you couldn't have negative values, then we could omit this whole part here, right? We could skip that. But since we do have negative values, possibly in the tile map, sorry, kicking the camera there, then we need to do that. Okay, so that's that one. Next thing we're going to do is index to chords. And we get an index, and we're going to return some chords. And this time we're returning an option of that, because there might not be any chords there. So we can do self.cells.get index. That was quite easy, wasn't it? Except that doesn't exist, so we'll make that. Self index, that will return an option, reference to cell, self.inner.get index. There we go. We're just exposing that function there. Apparently it was not happy about that, right? Because that's possibly some cell occupied chords. Some chords. Otherwise, any other outcome is none, because you might have an empty cell, so the index might exist, but it's an empty cell, so it's still not giving you chords back. So that's our index to chords. Apparently not found a reference. Okay, well then we'll just dereference that and be done with it. Okay, great. So next up, local position to index and index to local position. Let's do that. We'll start with local position to index. And that's going to be a position, which is a vector 2, and we'll return an index, which is usize. So it's important to know that there's a difference between coordinates and position. A local position even, is a set of x and y values, which chords are as well. But chords are tiles, right? So -1 would be a tile at -1. That doesn't cater for the size of the tile, right? So that was really bad, really poor explanation. The function will probably explain this better than I did. So we're gonna start by converting our position to coordinates, and we can do that by simply dividing the x value with the tile size. So plus x divided by tile size x, and because we need to call floor, because you can end up on you can have a tile that's on 0, 0, and then if you floor it, as long as you're within the tile size, you'll be fine. But then if you don't floor it and you go to -0.1, then you're still gonna end up, still gonna look like you're on tile 0. But by flooring it, we're gonna go to the closest value. So then you would end up on -1 instead. All right. And then so we're gonna do this, and then of course we're gonna do the same thing as we done up here. We are gonna deduce that, so let's yank the whole line there, go to the end and put that in. I want a space there, and we do the same. Whoops, we do the same thing for y. There we go. So that gives us the x and the y values, and now we just need to do the same multiplication here. We just need to do that, and then we can return index as usize. I think that's right. That will be our local position to index, and now we need to take my hand off my mouth. I'm talking, sorry. Now we need to do our index to local position. Okay, so let's do that. Index to local position. Self index is a usize. And return a... Can we return a vector too? No, it has to be an option vector, because you might not have anything at that index. So if let's match self.cells.get index. Do something, any other outcome, do return nothing. So whether it doesn't find one or whether it's empty, we return nothing. So now instead we shrunk the local position. Shrunk is a kind of wrong word, but we snapped the local position to the cell. Now we need to go the other way around. So we need to expand the coordinates we found to the tiles position, right, on the scene. So let's do x is caused x times self.cell, no, tile size x, and then we have to add tile size x divided by 0.2. We are replace x with y. There we go. So right, yeah, we need to this part of the equation will get us the top left corner of the tile, and then we need to add half a tile, so we end up in the middle. So that way we can get the middle of a tile and place something in the middle of the tile, because when we move our units, we're not going to want them to be in the top left corner of the tile, right? So we got that. So we're going to return an option, sum vector to new x and y, and I think that's it. Okay, so this is everything except valid exits. Okay, so right, let's do that next. Let's add valid exits. All right, let's add valid exit. It says exits here, but it's supposed to be singular, right? So and we're checking if we're checking coordinates. And if they're okay, we're going to return usize, which is our index. So we're using the valid exit to find out, when we do the pathfinding, whether a tile has valid exits around it. So let's do this by getting the index first. So we do chords to index. And then we say if no, match statement. So, okay, I'm jumping the gun a little bit here. So match self.cells.get index. And if we do have something, then we can return an index. Any other outcome, return nothing. And let's add that and tidy that up. Okay, so that's valid exit. Now quickly have a think on this. Is this right? So we get the coordinate, we get the index for those coordinates, and then we, because this might just be a complete nonsense, right? This might not be a valid index, so therefore we check if it is, and if it is an actual value in there, then we return it. So we only return a valid index if there is if there's somewhere to go, right? Okay, that's it for this one. So next up, we're going to implement base map, and this is part of something called bracket lib, which is going to do the actual pathfinding for us. So let's implement that now. So the first thing we're going to do is we're going to do cargo add bracket pathfinding. So we have the actual bracket lib. So now we have the base map. So implement base map for map. And we're going to have to implement two functions. They are the distance. Okay. Let's see if we can go here. There are the available exits and pathing distance. That's what it's called. Pathing distance. Okay, right. So we can start with this one. This one is going to need to get two coordinates. Coords one is self.get chords to index. No, it's index to chords. We need two of those. So this one might return none. So, but we have to return a floating point value. So we are going to unwrap this. And hopefully this will not be called with indices that doesn't exist. This will be called with the indices we get from calling get available exits. And get available exits will check if it's a valid exit, and if it isn't a valid exit, then it should not call pathing distance. Okay, so let's finish this up by calling distance alg squared dot distance 2d, and we'll pass in, we need to pass in point now. So chords 1.x si32 chords 1.y si32, and change that to that one. Okay, let's see if this builds. It does. Okay, next up we're going to implement get available exits. Okay, so I've opened the bracket lib pathfinding GitHub page, so I can see what the code is for get available exits, because we can just copy this. We can almost copy this. There's a few things we need to change. First of all, this might fail, and it's indexed to chords. And if there's nothing there, then we're going to return exits. No semicolon. And this is not a small vec for us. We don't have small vec, so let's take that out. And what else do we have? Okay, so now we have to change this. Okay, valid exit. Our valid exit takes one argument, not two. So we're gonna change this to be a plus sign. And then we can change our point to be a vector 2. And last but not least, we need to change these to be floating point numbers. And that guy too. Okay, so this way we can get available exits, but there's something missing. We are only getting the available exits that are in each cardinal direction, north, east, south, west. But we want to get all the diagonal ones as well. So we're gonna just increment this to 1, 1, 1, and let's see, -1. There we go. I think that's it. Okay, the one more thing we need to do. We need to change the cost for these to be 4. Okay, and I think that's it for now. Alright, next time we're going to add A-star pathfinding and add some tiles and some units and see if we can move them around a little bit. But that's it for now. Thank you.